We're looking here at the AP questions for the 2016, number 2, and that has to do with this equation. It starts off here in the bottom, and we can see that this is sodium bicarbonate, and this is acetic acid, which is vinegar. So everybody's talked about this all the time, baking soda and vinegar, and we know that it bubbles up and use it for put some food coloring, make it into the lava for a little volcano, stuff like that. And what's happening is that the two things combine, and we get the sodium with the acetate. That's just going to be a soluble compound. And we get the hydrogen with the bicarbonate. We get H2CO3, which breaks down into H2O and CO2. So that's the basis for this question. So let's go back and see what's going on. Okay, a student designs an experiment to study the reaction between sodium bicarbonate and acetic acid. The reaction is represented by the equation above. The student places 2.24 grams of sodium bicarbonate in a flask and adds 60 milliliters of 0.850 molar acetic acid. The student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. Identify the reaction represented above as an acid-base reaction, a precipitation reaction, or a redox reaction. Justify your answer. Well, certainly it is not a precipitation reaction because we're not making any solids. Okay, so we know it's not that one. Okay, now is it acid-base? Yes, it's an acid-base reaction, and we can see what's happening is that this H here is going to go over to the bicarbonate. So the H plus ion from acetic acid goes to the HCO3 minus and turns into H2CO3, and H2CO3 decomposes into H2O and CO2. So that's what we say. Yes, it's an acid-base reaction, and there is a proton, H plus, transferred from the acetic acid, okay, to the bicarbonate ion. Okay, and that's what makes it an acid-base reaction. It's a Bronsted-Lowry acid base, proton donor, proton acceptor. If you were going through the process of elimination, you could also say, well, it's not a redox reaction because none of the oxidation numbers change during this reaction. Everybody has the same oxidation number as a reactant as a product. Okay, based on the information above, identify the limiting reactant and justify your answer with calculations. So now we're going to go use these numbers. We have two different chemicals here, and we want to see, well, which one is going to run out first. So let's just take the 2.24 grams, and that's the sodium bicarbonate. Now, if we go ahead and add a sodium, which is 23.99, 23.00, plus a carbon, 12.01, plus 3 oxygens, which would be 48.00. Okay, we add those all together, and we get 84.0 grams. And that's 1 mole. Now, if I'm going to do this, I say, well, I would just pick either, say, for every mole of this that I form, I'm going to get 1 mole of reaction. I could do it that way. Or I could just say, I could figure out one of my products, like CO2 or H2O. But let's just start here with the number of moles. So if I calculate this, we get 0.0267 moles of sodium bicarbonate, which would be that same number of moles of each of the 3 products. Okay, next one here would be the, what do I have? 60 milliliters. So 60 milliliters of our acetic acid solution. Okay, I know that there are 1,000 milliliters in 1 liter. And I have my molarity, which is 0.875 moles of HC2H3O2 per 1 liter of solution. And if I do all this number, so 60 divided by 1,000 times 0.875, we get 0.0525 moles of acetic acid. Okay, so back here, it takes 1 mole and 1 mole, so there's a 1-to-1 reaction. So if I have this many moles, I'm going to get that many moles of reaction. This many moles of this, I'll get that many moles of reaction. Okay, I could say that that's how many moles of any of the products I have. So whichever one is smaller, that's the one that is my limiting reactant. So my limiting reactant is the sodium bicarbonate because it has a smaller number of moles. Okay, so for part C, says a student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions between the reactant particles. So as the reaction goes on, okay, the number of reactant particles is going to go down because it gets turned into products. And if there are fewer and fewer reactants, then we're going to have fewer collisions between the reactants, between the sodium bicarbonate and the acetic acid. Because there are fewer collisions, then we're going to have a slower reaction rate. Okay, now let's go back a little bit. This explanation right here, this was worth 1 point just for doing that much. And if we go back up here, okay, just for identifying that this was an acid-base reaction, okay, that was worth a point with a good explanation. And the explanation was either a process of elimination, eliminate those two, or saying that we got protons transferred. Okay, there were no points given for like an acid and base turns into a salt and water. Here's a salt, here's water. That really wasn't good enough, okay, because we really had to talk about, well, how does this work? It's not that kind of an acid-base reaction, so you had to talk about proton transfer to get that point. And that was 1 point. Second one was, oh, I'm sorry, I'm wrong. Okay, so you did get 1 point here just for saying that's an acid-base reaction, and then you got another point for the justification, so talking about the proton transfer. Okay, here, if you got to the idea that the sodium bicarbonate, is the limiting reactant, that's worth 1 point. And to do that, you had to calculate the moles of each of those two reactants so you can compare them. And so that was worth a point. So we have 1, 2, 3, 4 points, and 5. So 5 so far. Okay, now in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering that the flask gets cooler. So since the flask is getting cooler, then we know that the delta H is a positive number, that this reaction occurs, we're absorbing energy. What drives the chemical reaction between sodium bicarbonate and acetic acid? Well, okay, enthalpy having a positive enthalpy, positive delta H, that is not going to drive the reaction because things tend to go downhill potential energy-wise. They tend to, exothermic reactions would drive it, not endothermic. And so this guy is actually willing to go uphill because of entropy. So this is actually entropy-driven reaction. And what drives a reaction? What causes it to go? So is it going because the energy is doing it? Is it going because it's getting more disordered or entropy? Or is it both? And it's, enthalpy is going the wrong direction, so it has to be entropy only. Justify your reaction in terms of delta G. Okay, for a spontaneous reaction, for a reaction that is thermodynamically favorable, okay, delta G must be negative. Okay, that's just, the way that's just the definition of how delta G works here. So it's got to be a negative value. So if we were talking about delta G is equal to delta H minus T delta S, okay, if we're saying that delta H is positive, well, then that's going to make the delta G positive, and that's not good. Okay, so it must be the delta S. Okay, so since it's minus T, and that's temperature in Kelvin, that's always a positive value, delta S, the delta S must be positive and large enough, with a large enough temperature, so that when you get the T delta S, minus T delta S, that's going to make this guy negative. It's going to make the delta G negative. So it must be the entropy, positive entropy, getting more disordered. That must be the situation that is causing this reaction to go. And we know that because we're putting a solid and aqueous and we're forming a gas, CO2 gas. So that is the positive delta S that we're getting here. You know, it's getting much more disordered. Okay, now for bicarbonate, let's go back real quick. This is 1 point for just circling the entropy, and 1 point for the justification. Okay, and again, we're talking about the fact that this must be negative, delta G must be negative, and it's not the positive delta H that's going to make it negative. It has to be the positive delta S, so that's why the entropy will cause this reaction, cause this delta G to be negative, cause this reaction to be thermodynamically favorable. Okay, back here to bicarbonate ion. Okay, bicarbonate HCO3 with a minus charge. So what's going to happen, the carbon's going to be in the middle, and there's going to be oxygens on 3 sides, and on one of those oxygens there's a hydrogen connected. So here's what we have carbons and we have oxygens. So let's go ahead and give everybody an octet who wants an octet, and if I do that, then I've got 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've drawn 26 electrons. And what do I have? I've got a carbon which has 4 valence electrons and 3 oxygens. So I've got 4 plus 3 times 6, which is 18, plus hydrogen, that's 1, plus I have a negative charge on this whole thing. So that's going to be 1, so I have 24 electrons. That's how many I have to play with. So if I have 24 electrons, then this cannot be the correct picture. What's going to have to happen is I'm going to take away one of these pairs of electrons and these pair that only count for 1 atom at a time, and I'm going to replace it with a double bond, okay, that is going to count for both the carbon and the oxygen. Now, the fact that I made a choice, you know, I did carbon with this oxygen, I could have done it with this oxygen, then that means what's going on is we really have resonance. We're going to have 2 different structures. So I'm going to go back and clean up my picture a little bit. So what do we have? We have carbon doubly bonded to an oxygen, oxygen with a hydrogen, and singly bonded to another oxygen. I have 2 lone pairs here, 3 lone pairs here, 2 lone pairs here, and the whole thing has a bracket and a negative charge. And then I get another one, and I get a double bond to the left, single bond to the right, where I have the single bond, I have 3 lone pairs, double bond gets 2 lone pairs, oxygen bonded to a hydrogen, okay, and it has 2 lone pairs, and this whole thing also gets a negative charge. So that is the correct Lewis dot structure, and it says do a diagram or diagrams. It's kind of a hint that there's resonance happening here. And this was worth 2 points. Okay, one for getting the correct structure, the correct Lewis structure, and the other one was for showing that there's resonance. So even if you had an incorrect structure, if you were showing that there was resonance between them, then I think you got 1 of the 2 points there. Okay, then F says a student prepares a solution containing equal molar amounts, so equal moles, of acetic acid and sodium acetate. The pH of the solution is measured to be 4.7. The student adds 2 drops of 3 molar nitric acid and stirs the sample, observing that the pH remains at 4.7. Write a balanced net ionic equation for the reaction between nitric acid and the chemical species in the sample that is responsible for the pH remaining at 4.7. Okay, the fact that we have the pH remaining at 4.7, okay, and that we have equal molar amounts, that means equal moles of those 2, hopefully we realize that this is a buffer. Okay, and if we have a buffer, then what we really have is just the dissociation equation of a weak acid. And that's going to break up to be H plus and acetate. So what's happening here is that when we, remove a little bit of H plus by adding some base, then there is a donor right here. Oops, donor, let me go back and fix that. Donor molecule, which can put those H pluses back. And if I add some H pluses like we're doing in this question, then here I've got an acceptor, okay, which is my Bronson-Lowry base, and that can mop up any excess H pluses I put in. So I've got an acid and I've got a base, together in the same solution, equal amounts of those two. So we say if I were to put in some acid, so I'm going to add more H+, and that does not change the pH because this acceptor is there to pick it up. So we want to write a balanced net equation for the reaction that does this. So what are we talking about? We're talking about HNO3. If that's added, it's going to react with the sodium acetate. Now this is my molecular equation, and I'm going to go back and make it into an ionic. Okay, and what I'm going to get acetic acid and sodium nitrate. Well, this is very soluble. Sodium compounds, nitrate compounds are very soluble. That's a weak acid that's going to stay together. Here's a sodium compound, so that's going to break up into ions. And we should memorize that nitric acid is a strong acid, so that's going to break up into ions. So this is going to totally break up. This is going to break up. This one's going to break up, and that stays together. So what happens, I'm going to get rid of my sodium ions. I'm going to get rid of my nitrate ions. And my final equation is going to be H+ plus acetate turns into acetic acid. And this is my balanced net equation for why adding acid to this does not cause the pH to change, because this acceptor over here is going to react with those H+, turn it back into acetic acid that mops up those excess H+. And that is the entire equation. So this is worth 1 point. Just for getting this equation, and I believe that that is all 10 points. So we have 1 on F. Okay, we got 2 up here on E. We had 2 more here on D, so that's 5. And then we had 1 on C, 2 on B, and 2 on A. That makes 10 points altogether. And that is question 2.